Okay, so we figured out what the total force would be if we had to pull from 60 degrees from perpendicular, and the torque needed to be 35 Newton meters, okay? And so now it's saying what force is applied when the same wrench is used with 35 Newton meter torque is applied an angle of 75 degrees from perpendicular. So our torque is still 35 Newton meters, and the angle is now 75 degrees from perpendicular instead of 60 degrees from perpendicular. See, this is what's really nice and convenient about solving symbolically before plugging in your numbers, because we've already rearranged this equation. We already know that force in this situation is torque divided by cosine theta r. Okay, the same wrench, so our torque is 35 Newton meters, cosine of 75 degrees, and then our distance is 0.25 meters. And something I didn't point out before, force is in newtons, and we see this here because we have units of meters, and they cancel, and the only units we're left with is newtons. So I'm going to plug that into my calculator. I'm going to take 35 divided by the cosine of 75 multiplied by 0.25. And that gives me 540 Newton. Okay, so that would be the force necessary in order to be applying at this angle. Now, if we think about this, looking at this image here, it is the perpendicular component that turns the lever arm, right? And our angle is going from 60 to 75. So think of what happens to that perpendicular component if we just change the angle, but we don't change the force. See how this would go down, right? Because the angle would be getting bigger, and that would make the parallel component greater and the perpendicular component smaller. So to compensate for that greater change in angle, we need to increase the amount of force that we're applying at that new angle. And we see that. Okay. Now, let's look at the next examples here. Okay. And they're really not too bad at all. I think we're starting with something relatively simple, which is good. It's always good to start a unit that way. And let's see if we can get through these example problems in this video. So, consider the man pushing the playground merry-go-round in the figure to the right. He exerts a force of 250 newtons. I added a decimal point in there. If you could add that to your notes as well, I'd appreciate it, because then we're going to be working with 3 sig figs. At the edge of the merry-go-round and perpendicular to the radius. So this force, he's pushing at the edge, so that's the lever arm there, right, from the center, but that push is all tangential or perpendicular to that lever arm. Okay, and so we don't have an angle that we're having to plug in. We know that the perpendicular force, it's good to write this down, that force perpendicular is 250 newtons. Okay, how much torque does he produce? Assume that the friction acting on the merry-go-round is negligible, saying that there's nothing trying to pull it back, that the only force that is perpendicular to the lever arm here is the force that's being pushed. There's no friction trying to pull it back. Okay? So torque is equal to force perpendicular times by r. The radius is the 1.5, so that'll be the r, that'll be our lever arm there. And so we're going to take our 250 newtons multiplied by 1.50. Oops, let's multiply that. 375. Now, 375 what? Like, what are our units? This is torque. It's a force multiplied by distance. It's newtons multiplied by meters, and that's what we see in our units. Newton meters. Okay. All right, next. Example number 3. So we're still working on the car, so we're going back to example number 1. We're referencing example number 1 here. We're still working on our car. In this case, what force is needed if it is applied at a point perpendicular to the wrench? So recall, a bolt on a car engine needs to be tightened with a torque of 35 newtons, and you're using a 25 centimeter long wrench. So it's saying, instead of us being at an angle, right? So like if I were to redraw this. So instead of my force being at an angle like it was before, what if it was all perpendicular? What if my force in its entirety is equal to the force perpendicular? Okay. In this case, what force is needed if it is applied at a point perpendicular to the wrench? Okay. How long is the lever arm, and how much force do you exert? And that's what we're going to solve for there. So lever arm, again, it's from that point of rotation to where we're applying the force. And this is the 25 centimeter long wrench, but we want to be in meters. So the lever R, or that radius, is going to equal 0.25 meters. We know that torque is equal to 35 Newton meters. And we're going to solve for force perpendicular, which is the force. So torque is equal to force perpendicular times by radius. We're solving for this, so I'll just divide by R. Oops, backwards. And so let's plug that in then. So we're going to take torque, which is 35, divided by 0.25 meters, and we get a perpendicular force of 140 newtons. Okay, so this is interesting. This is the exact same situation, right? But the first time when we were pulling or pushing at 60 degrees, we had to use 280 newtons to produce 35 newtons of torque. And when we were at an angle of 75 degrees, we had to use 540 newtons, significantly more force, in order to produce the same amount of torque. But if we're going to push all perpendicular, and we don't have the angle component from perpendicular, then we only have to use 140 newtons for the exact same amount of torque. We'll have the same rotational capabilities on the wrench. Okay, our last example. If torque is 110 Newton meters is required, so if a torque of 110 Newton meters is required, and the largest force that can be exerted by you is 270 newtons, what is the length of the lever arm that must be used? Okay, so let me check my time really quick. We're good. We are only capable of exerting 270 newtons. And we know that torque is force perpendicular times by the radius. So we don't want any component of the force to be parallel. We don't want to waste any of our 270 newtons on a parallel force because that doesn't rotate it, right? We want it all to be perpendicular because that's where we're capable of producing the most torque. Okay, so this 250 newtons, if that's all that we're capable of, we're going to put that force all perpendicular to the lever arm. So our force perpendicular will be the 270 newtons. Okay. The torque that's required is 110 newtons, and we want to know the lever arm. Okay. So our torque equation, we're going to rearrange this to solve for R, so we'll divide by force perpendicular. And I'll plug in those numbers. The torque is 110 Newton meters divided by the force, which is 270. And so that means our lever arm, 4 sig figs, 3 sig figs, so my final answer will have 3, so it'll be 0.407 meters. Okay, nice. So that's individual forces that produce a torque. And next time we're going to discuss when there's more than one force acting on an object. So if I'm trying to rotate this pen and I push it here, but then I'm also pushing it here, and multiple forces causing something to rotate. That's going to be next time.